Okay, I think we can get started. Okay, so today what we're going to do is we're going to look at another exact solution to Einstein's equations. Okay, so we found one that was exact, which was the Minkowski metric. And that was good because that makes a connection between general relativity and special relativity, right? In the approximation of extremely weak gravity, or where we can turn off gravitational fields, we get Minkowski's spacetime and the usual laws which transform under the dictionary of Lorentz transformations. Now what we're going to do is we're going to find another solution to Einstein's equations. But since Einstein's equations are so complicated, we've seen that they're highly nonlinear, okay, and this second order differential equation. It helps if we can identify solutions with certain symmetries. Okay, so we want to classify solutions based on their symmetry properties. So the way we talk about symmetries is through something called killing vectors. Okay, this is quite a detailed topic in itself to talk about killing vectors and killing vector fields. Okay, I don't think we'll have time to go over all of those details, but I'll try to give you the basic idea today, okay, of what killing vector fields are and how we can use them to get a solution. Okay, and essentially a killing vector field gives you some idea of what the symmetries are of a given metric. Okay. So let's just look at some intuitive definition. Okay, and then after we understand killing vector fields, okay, we'll talk about a particular solution called the Schwarzschild solution, where we talk about rotational symmetry. Okay, okay, so let's begin. So what we'll do is we'll consider a manifold M. Okay, and this manifold M doesn't necessarily have a metric, so this is just a manifold, not necessarily a metric space, and it has a vector field X on it. So a vector field X means that at every point, so if there's a point R, there's a vector XR associated with that point. Okay, this vector field is smooth over the entire manifold. Now, so for example, if I have the point P, there's a vector XP. If I have the point Q, there's a vector XQ. Now, what we can do, and this is something that I had told you in the beginning of the class, but again, we didn't show rigorously, is that there is a sense in which we can think about an infinitesimal displacement generated by the vector field X. Okay. Now, that seems a bit strange to think about because really the vectors X live on the tangent space. They don't really live on the manifold themselves. Okay. But for infinitesimal displacements, you can think about going along the manifold, okay, in the direction of the tangent vector. Okay, so I'm not showing this rigorously, but I'm just giving you some kind of intuitive idea. Okay, so for example, like on a sphere, the tangent space at this point is, let's say, the tangent plane, okay, like this. But if I think about a tangent vector in this direction, I can think of it as generating infinitesimally small motion of this point to some point along this on the sphere itself. So again, I'm not showing this rigorously, but now instead of this transformation from P to P prime happening just at one point, okay, and so the important point is that this P prime is infinitesimally nearby, okay, so it's that infinitesimalness is controlled by an additional parameter which we call epsilon, and epsilon is a small parameter, okay, small dimensionless parameter. And now we think about the infinitesimal displacement generated not just at P, but at every point. For example, the displacement at R to some other point R prime, the displacement at Q to some other point Q prime, where each of these displacements is an infinitesimal displacement by the same epsilon amount in the direction of the tangent vector, or sorry, this vector X at that point. Okay, so the X vector at each point is generating sort of a flow. Okay, and epsilon quantifies how much we're moving along with the flow. Okay, so this is nothing but a diffeomorphism. Okay, this is a diffeomorphism in the sense of an active diffeomorphism, in that it's a map under this flow. Okay, the manifold, every point on the manifold. Okay, so this flow can be regarded as a mapping from points on the manifold to other points on the manifold, and it's always unique. Okay, this mapping is unique. And it's also invertible. Okay, so this mapping will denote as sigma epsilon is a one parameter diffeomorphism. Okay, so epsilon controls the size of that diffeomorphism. Okay, sorry, just give me a second. I'm going to turn off the fan because there's some P prime. Okay. Okay, so now let's imagine that you've generated this flow, or if you had generated this flow, the point P would have been moved to the point P prime, okay, under this transformation. Okay, so this is just telling us where you would have moved to under an epsilon flow. Now what we can do is we can relabel the coordinates of P prime, okay, and similarly the coordinates of Q prime and the coordinates of R prime. We can do a coordinate transformation. Okay, that is, we can do a coordinate transformation such that P prime. So if previously P had coordinates x, okay, and then P prime has coordinates x mu plus epsilon times capital X mu of P. Okay, so let me just write that clearly. Okay, sorry. Yeah, so what we can do is now we can write down, so suppose P had coordinates. So this was the manifold. This is the point P, and I'm going to exaggerate the distance to P prime. It's only infinitesimally far away. Okay, so we'll say P has coordinates x mu, and this is a vector capital X mu, or capital X, and in components, capital X has coordinates x mu partial x mu. Okay, then the point P prime has coordinates x mu plus epsilon times x mu. Okay, capital X mu, where capital X mu are the coefficients of this vector x. Okay. So this is, you can rigorously show what it means, okay, to, or give a rigorous definition to this flow, but in coordinates, okay, this is what that flow is. Okay, so so now what we're going to do is, this is the point that you would have flowed to. Okay, this is the point P, this is the point P prime. Under an epsilon flow, this is the flow of P to P prime. Now what you can do is you can relabel the coordinates of P prime, okay, as x mu. Okay, so we relabel the coordinates of P prime as x mu. So in coordinates, what we have done is the old coordinates of P prime are x mu plus epsilon x mu. The new coordinates of P prime, we just assign the coordinates x mu. Okay, this, we're free to make this coordinate transformation. Okay, and this coordinate transformation, by definition, is it has to be one-to-one. Okay, and this transformation is one-to-one because the forward flow generates a one-to-one transformation. So for every P, there's a unique P prime. So for P prime, we're labeling it by the coordinates of P. Okay, so therefore you can always do this. Okay, you can always relabel the coordinates of P prime as xp. Okay. Okay, so so now all we've done is said that there are two different situations. Okay, there's the situation where we have the original manifold. The original manifold has points P and P prime. We're not yet making a flow. We're saying that it is possible to make a flow. And if you would make the flow, then P would have flowed to P prime under an epsilon flow. Okay, what we're doing now is we're saying the point P prime that you would have flowed to, let's relabel that so that it has the coordinates of the point P. Okay. So now let's consider a tensor field T, okay, on M, and this tensor is of type RS. Okay, so R vector-like indices, S dual vector type indices. And now what you can do is you can define something interesting. See, after this transformation, Okay, so we're saying now that there's a tensor field everywhere. So the tensor field has some value at the point P, the tensor field has some value at the point P prime. Okay, and now what we're saying is after this transformation, okay, the point P prime has the coordinates x mu, and the point P has the coordinates, well, it has some other coordinates, okay, but now this has the coordinates of x mu. Okay, this is after a coordinate transformation. Okay, so you still have the same tensor TP prime here. Okay, and what you're going to do now is because now you can compare TP prime, okay, with this TP, okay, if the transformation is a diffeomorphism. Now, why can you do this? Okay, what we had argued earlier is any tensor that is defined at the point P prime that lives in a different tensor space. Okay, for example, if you think about a vector lives in a different vector space. The vector space is P prime. This vector lives at the point P. Okay, what we have really done, okay, when we say that there is a comparison between these two, is we are thinking about the inverse flow. Okay, so we're thinking about the inverse flow where P prime gets, we flow under minus epsilon and P prime gets moved to P. As P prime gets moved to P, TP prime gets moved to the point P. Okay, this is TP prime moved to the point P through a coordinate transformation. Okay, you can think of it as either happening through a coordinate transformation, or you can think of it as happening through this flow. Okay, that's what a diffeomorphism is. If you think about it as a flow, it's an active diffeomorphism. If you think about it as a coordinate transformation, it's a passive diffeomorphism. Okay, so what we can do is we can evaluate this. So if we think about it in terms of a flow, what we're really doing is we're taking TP prime here and we are asking what would happen as it flows back to this point. Okay, and then comparing it with TP. So this is called the pullback, okay, of TP prime. Okay, this gives you a tensor at the point P. Okay, it's taking the tensor at TP prime and bringing it back to the point P. Now, one important thing about this pullback is that it doesn't really depend on the coordinate. It doesn't really depend on the existence of a connection. Okay, so we said that to parallelly transport vectors, you need to have a connection, but this pullback doesn't require a connection. Okay, I'm not showing this rigorously. Okay, I'm just telling you this, but you can work it out or you can look it up in Nakahara. Okay, this is in chapter 5. It's easier to understand why this doesn't require a connection if we do it in this way. We'll do it in the sense of a passive transformation. Okay, so in the sense of a passive transformation, we think about the tensor TP at the point P. We think about the tensor TP prime at the point P prime. We make a coordinate transformation such that x mu plus epsilon x mu now has coordinates x mu. Okay, so now since this was a diffeomorphism, although this point is P prime, okay, this point P prime can be regarded, okay, as sort of as sort of being similar to P in the sense that now that we've made a transformation and given it the coordinates x mu, it's sort of what would have become the point P under that active diffeomorphism. Okay, so what we can do now is we can compare this TP prime after our coordinate transformation with the original TP at the point P. Okay, so we can make this comparison. This is the same as comparing the pullback of TP prime with TP. Okay, so what you can do is after this relabeling of coordinates of P prime, the coordinates x mu plus epsilon x mu to x mu. Okay, what you can do is now for this tensor field, you can define something called a Lie derivative. Okay, which I'll denote as Lx of t. It's the limit epsilon goes to 0 of the new TP prime minus the old t at the point P. Okay, so this is the new TP prime. This is the old t at the point P. Okay, and so this is and this difference will be small because if epsilon goes to 0, there's no difference at all. The point P and the point P prime are already the same. So in the limit epsilon is finite, Okay, sorry, in the limit epsilon is small, this difference will be finite. Okay, and whatever that difference is, that difference will be a tensor at the point P. Okay, so this difference will be a tensor. This will belong to the tensor space RQ at the point P. Okay, so this is the sense in which it's a Lie derivative. It's the difference between two tensors. Okay, at the same point under a diffeomorphism. Okay, and the entire reason you could do this is the comparison makes sense because the new tensor at the point P prime can be regarded as belonging to the same tensor space as that of P after you make the diffeomorphism. Okay, that is, after you make the diffeomorphism, P prime gets moved to P, and therefore it makes sense to compare two tensors, one at P prime, which has now moved to P, okay, and the original tensor which was already at P. Okay. Okay, and the important point is that the comparison can be made without defining any affine connection. You don't need to do anything called parallel transport. Okay, you don't need to define a connection on the manifold. You can just do this for general diffeomorphisms. Okay, and you can check under this definition, for example, the Lie derivative of a vector field, okay, is just the Lie bracket xy. Okay, and which we had defined earlier in the class. We had defined this Lie bracket of xy. So in components, the Lie bracket of xy, okay, was something like x nu partial nu y nu, okay, minus y nu partial nu x mu. All right. So the reason why this is not an affine connection is because if you consider the affine connection, okay, so this you can say, is this an affine connection? And the answer is no, this derivative is not an affine connection, okay? And that's why you can define it without defining parallel transport. So why is it not an affine connection? Well, it's not an affine connection because if you recall the property that the affine connection needed to satisfy, one property was linearity, which is I multiply, if I take x and I multiply it by some smooth function f on the manifold, then this should be f times del x y, okay? This was a property of the affine connection. But you can see that this Lie derivative is not going to satisfy that property because the Lie derivative will depend on not just derivatives of y, but also derivatives of x, the field with which you're taking derivatives of. Okay, so Lie derivative of fx of y will involve things like derivatives of f. Okay, so that's why it's not an affine connection. Again, I'm not going to spend a lot of time on these details. Okay, I'll just come to the point about how this Lie derivative connects to killing vectors. Okay, so now this Lie derivative can be defined for any tensor. So if given a vector field and given a tensor, okay, I can define this Lie derivative, and you can work out in components what it is with this definition. Okay. Now what you can do is, suppose you have a metric G on the manifold. Okay. Now you can define something called a killing vector field. So X is a vector field, and it's called a killing vector field if it's such that the Lie derivative of the metric is 0. Okay. That is, under this diffeomorphism, okay, under an infinitesimal diffeomorphism, which takes points x to points x prime. Okay. So I have a metric here, okay, which is the metric at the point x prime, okay, and I have a metric here, which is the metric at the point x. Okay, what we're saying is, after you make the diffeomorphism, okay, or rather what I do is I bring this point gx prime, okay, I bring this point x prime back to x by performing a diffeomorphism by minus epsilon, or equivalently I relabel the coordinates of x prime as x. Okay, when I make that transformation, okay, the metric gx prime, okay, this metric at gx prime, this changes. Okay, and what I do is I compare it with the metric coefficients for gx. Okay, and if I find that the metric coefficients are unchanged under this diffeomorphism generated by x, then we say that x generates an isometry. Okay, that is, under this diffeomorphism the metric has not changed. Okay, so then we say that this is an isometry. Okay, so it's easier to see this in components. Okay, so the components of G are left unchanged after this relabeling. Then we say that X generates an isometry. Okay, So that is, we say that this derivative is 0. So let's write it down in components. Okay. So this is the original metric at the point P. Okay, it's g mu nu of x. Now what we do is we take the metric at the point P prime. Okay, which has components g kappa lambda g x plus epsilon x. Now we make a tensor transformation. Okay, we make a tensor transformation. Coordinate transformation. Okay, and the coordinate transformation tells us the rule for how tensors transform. Okay, so at this point has coordinates x mu plus epsilon x mu. We change the coordinates to the coordinates x mu. Okay, we change it to the coordinates x mu. After we make this transformation, okay, the tensor transformation rule tells us, so if we're changing coordinates from some y to x, then we should have things like partial y kappa, partial x mu, and partial y lambda, partial x nu appearing in front. Okay, so that's exactly what I've done. I've put these factors over here. So this is y, okay, which is this, okay, and this is x. Okay, I've written it out in components, but let's think about what this means. Okay, so what we are saying now is that these are the components of a tensor. Okay, these are the new components of the tensor after we relabel p prime's coordinates as x. Okay, so what is the tensor? Well, the tensor is originally, before I relabel coordinates, it's g kappa lambda at x plus epsilon x. Okay, this is the tensor at g at p prime. Okay, is this times dx kappa dx lambda. Okay, what we are doing when we pull back, okay, or when we change coordinates, is we are changing this to a tensor. Sorry, I should also be a little careful. Okay, this dx kappa and dx lambda, these are defined at the point x plus epsilon x. Okay, and this is defined at the point x plus epsilon x. Okay, and now what we're doing is we're changing this tensor, okay, to something which we call the pullback, sigma minus epsilon gp prime. Okay, which is, it has the same its components transform under the tensor transformation law. Okay, so its components transform like this. Okay, so if I define this as y, and this is partial y, what we're doing now is we're saying let's transform these components. So that gives us partial y mu partial x. Sorry, let me write it like this: partial y kappa, partial x lambda, partial y, partial x mu, partial y lambda, partial x nu, g kappa lambda of y. Okay, and now what we're doing is we're saying that this is not a vector at x prime anymore. It's a vector at x. Okay, so I can use the basis for I can use the basis for this is the basis for dual vectors, and this is the basis for a dual 0-2 tensor. Okay, at the point P. Okay, so what we're saying, this is what we call the pullback of this G. Okay, so this G is evaluated at the point P prime. This is a tensor at the point P prime. And now what we did by this pullback is we converted it to a tensor at the point P. Okay, we converted it to a tensor at the point P. And once we've converted it to a tensor at the point P, we can now compare this with the tensor evaluated at the point P, which is G mu nu x dx mu dx mu. Okay, and what we want is that these components of this tensor Okay, so the difference between these two will be infinitesimal for small epsilon. Okay, what we want is that the difference between these two is 0. Okay, then we say that the lead, if the difference between these two is 0, then we say that the lead derivative of g is 0. Okay, that is, the metric is unchanged under this this diffeomorphism. Okay, so you can work out what this is in components. Okay, you can basically expand this, okay, to first order in epsilon. You expand it out to first order in epsilon, and what you'll get is an equation of this form. Okay, again, I'm not working through the details, but you can see why this would be true. So this, you expand it out, it would be g kappa lambda of x plus epsilon x mu partial mu g kappa lambda evaluated at x. Okay, so I will have terms like x mu partial mu g kappa lambda. Okay, that's this term. Okay, and then I'll have, from expanding out these derivatives to first order in epsilon, I'll have other terms which involve derivatives of x, capital X, where remember this capital X is the components of the vector field that you use to generate your diffeomorphisms. So that can vary from place to place, okay, because the vector field X changes from one place to another. Okay, so this is the equation that capital X satisfies. Okay, so in order for capital X to satisfy this equation, that is the lead derivative of g is 0, okay, under this transformation by x, okay, it must, the components of x satisfy this equation. Okay, and you can also show that the same equation can be written in terms of the metric compatible connection, okay, or the affine connection delta, okay, in this form. Okay, I'll leave this as a homework exercise. It's exercise 7.17 in Nakahara. Okay, this is a very important exercise, so please do it. Okay, I'll probably put it in the assignment as well. Okay, and you can write it explicitly in terms of the components. Okay, I can write it as gamma lambda mu nu. Okay, and I can expand this gamma lambda mu nu in terms of the metric, the Levi-Civita connection. Okay, that's the unique torsion-free metric connection. And what you'd find is that this equation is the same as this equation, which is the same as this equation. Okay, all these three are the same equation. Okay, and all of them are really coming from just this original equation, which is saying that the metric components are unchanged under this infinitesimal epsilon diffeomorphism. Okay, so let me give you an example to just show you how to make sense of what we've just shown. Okay, so let's suppose that we have a metric. Okay, so let's imagine that we have our spaces R4, and in the Cartesian basis, g mu nu is eta mu nu. So this normal Minkowski spacetime. Okay, now in this Minkowski spacetime, gamma lambda mu nu is 0. Right? We already worked out the Christoffel symbols are 0 because the metric is constant. Christoffel symbol depends on derivatives of the metric. So the Christoffel symbols are 0. So let's take the Killing equation, which was in this form. Okay, partial mu x nu plus partial mu x mu minus something is 0. The Christoffels are 0. So for this particular metric, okay, the Killing equation just is this. Okay, the equation that the Killing vector field satisfies is just this: partial mu x mu plus partial mu x mu is 0. Okay, this has very simple solutions. For example, you can guess one solution very easily. Okay, so I'll guess solution. So I'll guess a solution and I'll label the solutions by I. Okay, so there is one solution which is a vector field, which means that I have to define its components at every point x. Okay, and so I labels which solution I'm talking about. Okay, so I is 0, 1, 2, 3 are 4 different solutions to this vector field equation. Okay, for each solution, I have to figure out all the components. So the claim is that one solution is there's a Kronecker delta nu I. Okay, so if nu is the same as I, then this is 1. If nu is not the same as I, this is 0. Okay, so what does that mean in components? So let's take the 0 solution. Okay, so T0, we'll write out T0 nu. This is a 4 vector, and this is a 4 vector. I mean, it's a vector at every point on the manifold. So at every point on the manifold, it's a vector, and it's a constant vector. It's 1, 0, 0, 0. Okay, so it's 1 along the partial t direction, 0 along partial x, 0 along partial y, and 0 along partial z. Okay, I'm just writing the coefficients of the vector. Okay, so T0 I can write as instead of writing it in this way in these components, I can just write it as 1 times partial t or partial t. Okay. So this quantity or these vectors which are written in this way, okay, more simply in terms of the expanding them in terms of basis vectors, t0 is just partial t. Similarly, t1 is partial x, t2 is partial y, t3 is partial z. Okay, you can check easily that this satisfies the killing equation, right? So it satisfies the killing equation because, for example, if I take t0, okay, I don't plug in partial t here, right? I'm plugging in coefficients of partial t here. Okay, so what I want is the coefficient. I want these coefficients, 1, 0, 0, 0. Okay, so I want to plug in those coefficients. So, for example, if I look at this equation, okay, let me take the x0 vector. Okay. Okay, so let me take the x0 vector. Okay, so x0 nu. What is x0 nu? What are the components of x0 nu with a lower nu? -1 will appear here. Okay, this is because, or sorry, I'm using, let's say, t0. Okay, so I'm plugging in t0. I'm saying t0 is a solution to this equation. Okay, and t0 nu is this. Okay, but I have to lower it with the metric. The metric is eta mu nu, so it just gets lowered to -100. Now what we're saying is, so this is t0. The 0th component is -1. t0, the first component is 0. t0, the second component is 0. t0, the third component is 0. Okay. Now it's easy to see that because this is a constant, it will automatically satisfy this killing equation. Okay. So you have 4 killing vectors. Okay. Now here's the important point about these killing vector fields. These killing vector fields are defined at every point on the manifold. Okay. So at every point on the manifold, this is partial t, but you have to remember that this partial t is taken at different points on the manifold. Okay. So what we're saying now is, imagine, let me just draw an xt, the xt plane. Okay. So forget about the y's there. So at this point, okay, on the manifold, there is a vector t0. Okay. T0 evaluated at the point x. Okay, what is T0 evaluated at the point x? It's partial t. That is, it's a vector which points along the time direction. Okay, it's a vector which points along the time direction. Now, we've said that this vector pointing along the time direction generates an infinitesimal diffeomorphism in that direction. Okay, or pointing in some direction generates an infinitesimal diffeomorphism in that direction. So in other words, what we're saying is the coordinates of x mu under that infinitesimal diffeomorphism become x mu plus epsilon times t mu, where t mu are the coefficients of this vector. Okay, so if we take t mu to be t mu I, okay, then we get epsilon delta mu I. X mu goes to x mu plus epsilon delta mu I. In particular, if we take t0, okay, which is this time translations, what we'll get is I is equal to 0. Okay, and what we get is x mu plus epsilon delta mu 0. Okay, x mu goes to x mu plus epsilon delta mu 0. That means only if mu is equal to 0, okay, this is t plus epsilon. For others, it's it just gives you x goes to x, y goes to y, and z goes to z. Okay, so this is the sense in which the vector partial t generates an infinitesimal diffeomorphism. What is that infinitesimal diffeomorphism? What it does is it generates time translations. Okay, it under this flow, okay, by an amount epsilon, t goes to t plus epsilon, x goes to x, y goes to y, z goes to z. Okay, so it's an infinitesimal translation in time. Okay, so time translation is an isometry of the metric. Why is it an isometry of the metric? Well, if I look at the metric components at this point, okay, and I compare with the metric components at this point, so the metric components at this point are -1, 1, 1, 1. Okay, I have to sort of do what is called a pullback, okay, and bring this metric, which is defined at the point P prime, back to the point P, okay, under this flow. It turns out that when you do that, you will still get the same components, -1, 1, 1, 1. And now if I compare it with the original metric at the point x mu, I already had -1, 1, 1, 1. So the difference between them is 0. Okay, and that's why this is an isometry. Okay, time translation doesn't change the metric, okay, under this infinitesimal diffeomorphism. right? So, so time translation is an isometry. Okay, so the other transformations that we've written here, this is generates translations in space along the x direction. This is generates translations along the y direction. This generates translations along the z direction. Okay, in a similar way. Any questions at this point? Okay, let me show you a slightly more non-trivial example. Okay, in the same Minkowski spacetime of some other killing vectors. Okay, so this seems like a very trivial killing vector because the coefficients were constant. Okay, but remember they're constant only a certain basis. Okay, these killing vectors are defined no matter what basis you use. Okay, so if I have a different basis, I can always translate this T0 into that basis. But the fact that T0 is a killing vector field is a basis independent statement. Okay. So time translations translated to any other basis, okay, would be a basis independent statement. So for example, if I translate it to the Rindler basis, okay, and I ask what happens to this time translation, what does it look like in the Rindler basis, okay, when I look at it in the Rindler basis. Okay, so that is we make our transformation of coordinates from t, x, y, z, okay, to the coordinates eta, rho, yz, okay, where I mean, I hope you recall this, but t is equal to rho cos theta, and x is equal to sorry, I think it's wrong. T is equal to rho sin theta, x is equal to rho cos theta. Okay, so this is the dictionary that relates them. And now the point is that this partial t, okay, is a killing vector. Okay, this is a killing vector, and it doesn't matter which basis you choose to define it. So we can ask, how do we express this in the basis of partial eta and partial rho? Okay, or actually it turns out to be easier to think about expressing partial rho in terms of these killing vectors, okay, and partial eta in terms of these killing vectors. What you can show is that partial eta, okay, partial eta is equal to x times partial t plus t times partial x. Okay, and partial rho okay, sorry, I have to work it out. Okay, but let's just keep this one. Okay, and I'll show you what this one means. Okay, so this is a killing vector. Okay, and the killing vector looks non-obvious when you go to the Rindler basis. Okay, in the Rindler basis, it looks completely different. It's not obvious at all that this is a killing vector that is under this transformation. This generates a flow, okay, of coordinates, even in Rindler coordinates, and under that flow of Rindler coordinates, okay, the metric in Rindler coordinates remains invariant. Okay. Okay, so now what we'll do is we'll go back to Minkowski coordinates for a second. Okay, we'll go back to Minkowski coordinates, and we'll solve this killing equation, and we'll find some more killing vectors. Okay, and these new killing vectors, I'll show you that these are slightly non-trivial. Okay, so you can show, for example, that there's a killing vector, for example, this one. Okay, which is xt00. Okay, this is exactly the one I wrote down here, which is partial eta. Okay, partial eta in Rindler coordinates. Okay, this is a killing vector. Okay, why is it a killing vector? It's not obvious. Okay, that this is a killing vector, but let's see why. Okay, so if we think about what this does, in just like partial t generates translations in time for regular time coordinates, partial eta generates translations in Rindler time. Okay, Rindler time gets moved forward. But if we recall what Rindler time is, okay, Rindler time is this. Okay, so if you're over here, okay, Rindler time is this is increasing eta. This is eta prime. Okay, so what it does, it will take you from one point on this hyperbola to another point on this hyperbola. Okay, it will take you from eta to eta prime. Okay, over here. Okay, without changing your rho coordinate. Okay, so it's only changing eta, but it's not changing rho. So not changing rho means you stay on the same hyperbola. Okay, you only change eta. But what is this transformation? Okay, which is taking you from eta to eta prime. That transformation that's taking you from eta to eta prime is, if you have a Rindler observer with some velocity, this observer has a different velocity here. Okay, in as measured in the Minkowski inertial coordinates. So this is just going to be a boost. Okay, it's going to be a Lorentz boost. Let's see how this is a Lorentz boost. So in the original Minkowski coordinates, this is xt00. Okay, which we can write as x partial t plus t partial x. Okay. Now, if I lower the index, okay, so this is b1 upper mu. If I take b1 lower mu, it's minus x t00. So the first thing we'll check is that this satisfies the Killing equation. Okay, so if I take, for example, partial x bt plus partial t bx, okay, so this is one component of the Killing equation. Partial mu b nu plus partial nu b mu, so is equal to 0. So I'm checking for mu is equal to x and nu is equal to t, that this satisfies the Killing equation. So I have partial x bt plus partial t bx is 0. The left hand side is now partial x of the bt component is minus x. The bx component is t. Okay, so I get partial t is 0. Okay, so so this satisfies the Killing equation. Now you can ask what happens under what happens to my coordinates under this flow generated by this b1. Okay, so under b1, x mu goes to x mu plus epsilon b1 mu, which means that t goes to t plus epsilon times b1 mu is x, so it's epsilon times x. But at the same time as t goes to t plus epsilon x, x must go to x plus epsilon t. Okay, and y goes to y, z goes to z. But what is this? Okay, this transformation is really an infinitesimal Lorentz boost, right? Because in a Lorentz boost, t prime is cosh eta t plus sinh eta x. Okay, and if I take eta to be infinitesimal, cosh eta is 1, sinh eta is approximately eta. Okay? And similarly, x prime is cosh x plus sinh eta t, okay, which is x plus epsilon t plus eta t. So this is just generating an infinitesimal boost. Okay, so you see that under an infinitesimal boost, also the metric is invariant. Okay, so the isometries are just a way of realizing the symmetries of a metric. How do we find isometries? We find the Killing vectors, okay, or the Killing vector field. Once we solve the Killing equation, okay, the Killing equation was, more generally, it was expressed in this form. Okay, it was expressed in this form. Once we solve this Killing equation, we will get Killing vectors or a Killing vector field. Different Killing vector fields tell us about different isometries of the metric. Okay, so in the case of Minkowski spacetime, we get these four translations. Okay, translations in time, translations in space. We get 3 boosts. Okay, which similarly to this, okay, you can write down a boost along the x direction, boost along the y direction, boost along the z direction. So can you guess, for example, what is the boost vector, boost Killing vector, the components of the boost Killing vector along the y direction? What would they be? By analogy with this generates a boost along the x direction. Y 0 t0. Good. This would give you a boost along the y direction, and similarly a boost along the z direction, so the 3 direction would be z 0 0 t. Okay. Now similarly you can show, okay, that you can also generate rotations. Okay, and these rotation Killing vectors also solve the same Killing equation. Okay, for the Minkowski metric. Okay, so 0 y minus x 0. And if you ask, for example, what is the infinitesimal transformation generated by this Killing vector? T goes to t, okay, because this component is 0. X goes to x plus epsilon y goes to y minus epsilon x. This is nothing but an infinitesimal rotation, okay, by an angle epsilon. Okay, this is an infinitesimal rotation by an angle epsilon, right? Because x prime is x cos theta plus y sine theta, okay, and y prime is y cos theta minus y sine theta, sorry, minus x sine theta. Okay, so for theta infinitesimal, okay, and if I set theta is equal to epsilon, I will get exactly this transformation. Okay, so this is another set of killing vector fields. Okay, the rotations. Okay, and in polar coordinates, again, you can express this in different coordinates. So for example, Rz in polar coordinates can be written as partial phi, and you can show similarly that Rx can be written in a more nasty looking way, but cos phi partial theta minus cot theta sine theta partial phi. Ry can be written as minus sine phi partial theta minus cot theta cos phi partial theta. Okay, so this looks highly coordinate dependent, okay, but there are still some killing vector fields. Okay, however, it is possible to talk about killing vector fields independently of their coordinates, okay, in the sense that they will satisfy some important properties, okay, which is that if you compute their Lie bracket, okay, as we defined earlier, what the Lie bracket is. If you compute, for example, the Lie bracket of Rz and Rx, okay, you will get Ry, okay. You can show this much more easily in the Cartesian basis. Okay, you can show this much more easily in the Cartesian basis. Let me not work it out. Okay, it's a homework exercise. It's very trivial to show in the Cartesian basis. Rz Rx is Ry, Rx Ry is Rz, Ry Rz is Rx. Okay, so their Lie brackets basically are closed. Okay, in the sense that if I take the commutator of any two killing vector fields, sorry, this Lie bracket of any two killing vector fields, it gives me back a linear combination of other killing vector fields. Okay, so that's what we mean when we say the algebra of the killing vector fields is closed. Okay, that is the Lie bracket of any two killing vector fields gives me back some linear combination of the other killing vector fields. Okay, so it's this algebra, okay, of the killing vector fields that really gives you a coordinate independent definition, okay, of what the symmetries are. Okay, this algebra that these coordinate these killing vectors satisfy, this algebra of killing vectors, okay, it's called a Lie algebra. This Lie algebra of the killing vectors, okay. So this, for example, this algebra is called the algebra of SO3. Okay, it's the algebra satisfied by the generators of rotations. Okay, this is denoted as small SO3 to distinguish it from capital SO3. Capital SO3 is the group of rotations. Okay, small SO3 is in some sense similar to capital SO3, but it really has to do with infinitesimal rotations. Okay, so it's sort of the generators of infinitesimal rotations. So this is called the Lie algebra. Okay, if you studied sort of infinitesimal generators in quantum mechanics, okay, then this is really the algebra satisfied by those generators in quantum mechanics. Okay, small SO3. Okay, capital SO3 is the property, is the group. Okay, whereas small SO3 is the property satisfied by the infinitesimal generators. Have you seen generators of SU2 or SO3 in your quantum mechanics class yet? Yeah, you covered it. Okay. Okay. This idea is more general. Okay, it can be true for other groups. Okay, besides SU2 and SO3. Okay, so this algebra defines a symmetry. Okay, and the symmetry now is sort of expressed in a completely coordinate independent way. These two vectors, I don't care which coordinate basis I express them in, they will always give me Ry, okay, no matter which coordinate basis I use. So this algebra of these killing vectors is basically coordinate independent, okay? And I mean, even the killing vectors are coordinate independent, but of course, how you choose your killing vectors, which one you think of as time translations, which one you think of boosts, that is a coordinate dependent statement. Because as we've seen, if I switch to in Minkowski coordinates, this generates boosts, okay? But in Rentala coordinates, the same vector generates Rentala time translations, and Rentala time translations are boosts in standard Cartesian Minkowski coordinates. Okay, so how we physically think of it is coordinate dependent. Okay, but the algebra that these killing vectors satisfy, that is a coordinate independent statement. Okay. Okay, so now if we take the full Minkowski metric and ask what is the maximal set of killing vector fields that we can have, okay, it turns out that they're just the ones that we wrote down. You have 4 killing vector fields associated with space-time translations, 3 associated with boosts, and 3 associated with rotations. Okay, so there are 10 killing vector fields, 10 different killing vector fields, and the algebra that these satisfy is called the Poincaré-Lie algebra. Okay, the Poincaré-Lie algebra. It's the infinitesimal version of the so-called Poincare group. If I look at the subgroup, which is just the boosts and rotations, the boosts and rotations themselves are closed, okay, under their own algebra, and this generates small SO31, okay, which is basically the Lie group or Lie algebra version of the full Lorentz group, which is SO31. Okay, this is the algebra satisfied by the infinitesimal generators of the Lorentz group. If I include translations, I get the so-called Poincare group. Okay, so the general statement is that in D dimensions, okay, if I don't restrict myself to 4 dimensions, in D dimensions, if I have the flat metric, then I have D translations, okay, translations in every one of the coordinates. And how do I count my rotations and boosts? Well, I can think of my rotations and boosts as just being a transformation either in the, so for example, if I have T, X, Y, Z, okay, I can think about my transformations in Tx, Ty, and Tz. These are my boosts. And I can think about a rotation about the x-axis, y-axis, or z-axis. But instead of thinking about the x-axis, y-axis, or z-axis, I should really think about, in higher dimensions, I can't really think about a rotation about the y-axis. Okay, what I should really think about is a rotation in a plane. So I should think about rotation in the xy plane as that's what I would call a rotation about the z-axis in 3 dimensions. But in higher dimensions, the z direction is orthogonal to x, y, and w. Okay, so specifying a rotation about the z-axis doesn't make sense because it's not telling me whether that rotation is in the xy plane or in the xw plane or in the yw plane. Okay, so in higher dimensions, we should think about rotations, and even in 3 dimensions or 4 dimensions, we should really think about rotations in a plane. So rotations are defined by choosing a pair of these spatial coordinates. So I can think about rotations in the xy plane, yz plane, or zx plane, or x. I can think about xw plane, yw, zw, and so on. Okay. So similarly, by choosing any pair of the spatial coordinates, I get by choosing any pair of the spatial coordinates, okay, I get a rotation. By choosing any time coordinate with one of the spatial coordinates, I get a boost. Okay, so basically, I have to choose just any 2 of them. Okay, I'll either get a rotation or a boost. So that can be done in DC 2 ways. Okay, D choose 2, where this is D into D minus 1 by 2. Okay, that will give me the total number of rotations and boosts. So D into D minus 1 by 2 rotations and boosts, and D translations. These are the isometries of D-dimensional Minkowski spacetime. So if I add them up, D plus D into D minus 1 by 2 gives me D into D plus 1 by 2 killing vector fields. So in flat Minkowski spacetime, I have D into D plus 1 by 2 killing vector fields. For D is equal to 4, I get 10. Okay. So this is actually turns out to be the maximum number of isometries that you can have in any D-dimensional spacetime. Not just Minkowski spacetime, but any D-dimensional spacetime, you can have at most D into D plus 1 by 2 killing vector fields. Okay. Now it turns out that in D-dimensional spaces, okay, there are other spaces that have the maximum number of killing vector fields, but these other highly symmetric spaces are not necessarily flat Minkowski spacetime. So you can have other spacetimes, okay, which have many isometries. Okay, they have all these isometries, but they're not flat. Okay, so let me give you an example. In 2 dimensions, okay, if I take R2 with a Euclidean metric, so that is I just take Euclidean metric like this, okay, in Cartesian coordinates. This has the following 3 symmetries. Okay, so in 2D, our formula gives us D into D plus 1 by 2 is 3. Okay, so if D is equal to 2. So what are the symmetries? Well, there are 2 translations and there's 1 rotation that you can make. That's it. Okay, there's nothing else that you can do. There are 2 translations and 1 rotation. These are all the isometries of R2. But there are other spaces which have the same number of killing vectors. Okay, so if I take for example, the 2 sphere, okay, the perfectly symmetric 2 sphere, okay, with the usual metric inherited from embedding in 3 dimensions, okay, then this 2 sphere has 3 killing vector fields on it. It's hard to understand what those 3 killing vector fields are if you're on the 2 sphere itself. But if you think about the embedding of this 2 sphere inside 3 dimensions, though the killing vectors are easy to understand. They're just three-dimensional rotations. Okay, they're just three-dimensional rotations. So for example, if I embed this in 3 dimensions, x, y, z, okay, I can think about rotations, let's say about the x-axis, which is, think about rotations about the, let me think about rotations about the z-axis, okay, which are rotations in the xy plane, okay, or I can think about rotations about the y-axis, which are rotations in the xz plane, or I can think about rotations about the x-axis, which are rotations in the yz plane. Okay, if I express them in terms of coordinates along the sphere, okay, they become hard to visualize. Okay, but it's easy to understand by embedding this in 3 dimensions. Okay, but basically it has 3 killing vector fields. Okay, it has 3 killing vector fields. So this is also a maximally symmetric space. Okay. Similarly, you can also show that there's a space of constant negative curvature, which I told you can't visualize by embedding in 3 dimensions. Okay, you can embed in 4 dimensions, but that doesn't help you visualize it. And it also has 3 generators, okay, of 3 killing vector fields. So this I'll give you as a homework assignment, is to find the killing vector fields of this symmetric space, symmetric Euclidean space, space with Euclidean signature, that is all positive signs in the metric, but which has constant negative curvature rather than positive curvature. Okay, again, this has 3 killing vector fields. Okay, these are maximally symmetric spaces in 2D with Euclidean signature. I mean, these are all Riemannian manifolds. Okay, but it's possible also in 4D. Okay, similarly, by analogy, in 4 dimensions, it is possible to have other spacetimes which have 10 killing vectors, but these are not Minkowski spacetime. Okay, these have some different. So these are basically spacetimes with constant positive curvature or constant negative curvature. This curvature is harder to visualize because this curvature is 4-dimensional curvature, right? So it's harder to visualize. Okay, but these spaces, I'll just write down the name. They're called anti-de Sitter space and de Sitter space. Okay. This is anti-de Sitter space. Okay, these spaces are harder to visualize, but they all have 10 isometries, okay, or 10 different killing vectors each. Okay, so if it's in 4 dimensions, you call it DS4, okay, if it, or ADS4. Okay, and standard Minkowski space, let's say you can denote as M4. Okay, this Minkowski space is M4. Okay, these are spaces with 4 spacetime dimensions with that is with Riemannian signature, that is -1, 1, 1, 1 when I diagonalize the metric at a point. Okay, but they all have the same number of isometries, but they're different spaces. DS4 has positive curvature, ADS4 has negative curvature. Okay, so this is the analog of the 2-sphere, okay, except on a pseudo-Riemannian manifold. Okay, and this is the analog of the 2D hyperbolic plane, except this is now in again with pseudo-Riemannian signature. Okay, all of these are very hard to visualize. Okay, but so you have to individually work through each one to see what it is. Okay, I'm just mentioning this because these spaces are important. Okay, they show up in different places. De Sitter space. We believe that the universe that we live in is actually described by a de Sitter universe, or is approximately a de Sitter universe today. Okay, and so this solution is important in cosmology. Okay, and it's also believed that at very early times, during the very earliest instance in an epoch called inflation, the universe was approximately de Sitter. Okay, it had this de Sitter-like behavior. ADS space is important in the context of string theory. Okay, it has been shown that there is a duality between physics in 5 dimensions, which lives in anti-de Sitter space, and Minkowski space in 4 dimensions. Okay, it seems rather remarkable that this is true. Okay, because one is a 5-dimensional theory in a curved geometry, one describes something called quantum field theory in 4 space-time dimensions. But it turns out that the theory of this particular quantum field theory described in 4 dimensions gives you exactly the same observables. You can make predictions of all the observables by describing it by this 5-dimensional theory. So this duality is called the ADS-CFT correspondence, and it's turned out to be very useful in string theory. Okay, and in fact, it's a whole field by itself. Okay, which has been in development for the past 20 or 30 years. Okay, I'm not going to say much more about this. Okay, what I'm going to do is, now that we understand how to talk about symmetries of a metric, I'm going to talk about a particular solution, exact solution to the Einstein equations. Okay, so I should just say that these ADS and de Sitter are also turn out to be exact solution to the Einstein's equations. I won't discuss them. Okay, I'm going to discuss another class of exact solutions to the Einstein equations. Okay, I'll pause for questions. Sorry, I know this was not rigorous, but I hope this is making sense. Just let me know if you're confused about something, or if you want to go over those examples again. Yeah. So you have to be very loud. I can't hear you. Sorry, all I heard was in Rentala coordinates. Yeah, del rho is not a killing vector. Yeah, you can show that del rho is not a killing vector. The metric explicitly depends. Okay, yeah, that's another. Okay, that's another thing that I should point out. Okay, if your metric components. Okay, so let's imagine that this is your metric. Okay, this is G. Now, one important point is, suppose your metric doesn't depend on some particular coordinate. Okay, so let's suppose if I take the coordinate mu is equal to some particular value. Okay, let's say mu is equal to 1. So let's suppose that the metric does not depend on x1. Okay, then what you can show is that partial x1 is a killing vector. Okay, so if in some basis I can show that the metric doesn't depend on a particular coordinate, then that vector becomes that partial of x with respect to that coordinate is a killing vector. Okay, is a killing vector field. Okay, so I won't show this. I mean, it's quite easy to show. Okay, but so for example, our regular metric was -1, 1, 1, 1. Okay, and since the metric doesn't depend on t, x, y, z, partial t, partial x, partial y, and partial z are killing vectors. Okay, but this doesn't give you all the killing vectors. It only gives you some of the killing vectors. Okay, so basically saying if the metric in some coordinate basis is independent of some coordinates, okay, then it tells you that partial with respect to that coordinate is a killing vector. Okay, or is a killing vector field. Okay, so now what we're going to do is we're going to look at a particular solution of the Einstein's equations. Yeah. You have to solve the killing equation. If you solve the killing equation and find all the solutions, then you know all the killing vectors. Yeah, these ones you can find out by yeah. So what happens is if you have other killing vectors, for example, if I'm in the t, x, y, z, okay, I can go to a coordinate system. For example, if I switch to Rentala coordinates, okay, if you were somehow clever about guessing the coordinate system, in t, x, y, z, I can only figure out using this rule that partial t, partial x, partial y, and partial z are killing vectors. If I switch coordinates to Rentala coordinates, then my metric is this. Partial d rho square plus dy square plus dz square. In these coordinates, the metric is also independent not just of y and z, but also independent of eta. So that tells me partial eta is a killing vector. Okay. Similarly, if I switch to Rentala coordinates by making a boost along the y direction or z direction, I would have figured out partial eta corresponding to those directions is also symmetry. Okay. And so if I had made I would have to sort of cleverly guess a coordinate transformation such that in that coordinate system, okay, the metric doesn't depend on some particular coordinate. I can use that to figure out killing vectors. That is not true. That is not true. Oh yeah, so, okay, sorry, that the converse of the statement is this true is, that is, if this depends on x, yeah, I think the converse should also be. Yeah, I think that's right. I think that's right. So I think this converse statement is true. So if you find that partial x is a coordinate vector, okay, you have to be careful. What are you holding constant? Because that determines your basis. Okay, in that basis, then yes, the metric is uh, sorry, the metric should be independent of that coordinate. Okay. So now what we'll do is let's come back to our 3 plus 1D spacetime, okay, and we look for a solution to Einstein's equations. And the solution that we're going to look for is, first of all, it's a vacuum solution, okay, which means that we're solving with T mu is equal to 0. Okay, that is, we're setting the stress energy tensor to 0. The second thing is we are looking for spherical rotational symmetry, okay. That is, we have three rotational killing vector fields. Okay, how do we define what are rotational killing vector fields? Well, we're saying that there are three killing vector fields that satisfy that algebra that we had written down earlier. Yz is equal to x, zx is equal to y. Okay, so all we're saying is that there must be three killing vector fields. This is a basis independent statement that there are three killing vector fields that satisfy this property. Okay, we're solving for on a 3 plus 1D manifold. Okay, and asymptotically, our spacetime is Minkowski. Okay, these are the three requirements that we're making on our solution. Okay, now it turns out, okay, that there's a theorem called Birkhoff's theorem. Okay, which again I'm not going to prove this. Okay, is that any spherically symmetric vacuum solution to Einstein's equations, that is, if I have three killing vector fields that satisfy this equation, then there is automatically an extra time-like killing vector that you get. Okay, that is, you get a time-like killing vector field. That is, you get some partial t. Okay, that is, you get a fourth killing vector field for free. Okay, this is a time-like killing vector field. So this is called Birkhoff's theorem. Okay, so what that means is that if I switch to the coordinate system which uses this as a coordinate, okay, uses this time-like killing vector field as a coordinate, then your solution to Einstein's equations is going to be rather simple. Okay. So what we're going to do is, what we have to solve is we have to solve Einstein's equation, that is g mu nu is 0. Okay, the Einstein tensor is equal to 0, where the metric has the following killing vector field. It has T0, Rx, Ry, Rz as components, where T0, Rx, Ry, Rz are killing vector fields. Okay, and T0, let's say, defines some partial t. Okay, and it's convenient to go to polar coordinates, and in polar coordinates Rx, Ry, and Rz. Okay, we've already seen using Minkowski space. Okay, that Rx, Ry, Rz take this form. Okay, in those polar coordinates. So it's going to be convenient to work with the coordinates which are already defined. Okay, sorry, theta phi. The coordinates which are already defined by our killing vectors. Okay, so we'll have t, theta, phi, and r as our coordinates. Okay, and our killing vectors are these plus partial t. Okay, these are all our killing vectors. Okay, and yeah, so we want all our killing vectors. Now it turns out that because you have this rotational symmetry. Okay, so now I'm not going to show this. Okay, but it turns out that there's only one unique solution to Einstein's equations, which has this isometry. Okay, that is the Rx, Ry, Rz isometry. Birkhoff's theorem guarantees that you'll automatically have this extra killing vector. Once you have these isometries, the form of the metric gets quite restricted. Okay, so it turns out that there's only one class of solutions, okay, to Einstein's equations. So it's not just that you must have a metric. The metric must also satisfy now Einstein's equations. Okay, that's the additional constraint. constraint that you're imposing. Once you impose that it satisfies Einstein's equations, there's only one class of solutions. This class of solutions is called a Schwarzschild metric. Okay, this class of solutions only differs by a constant. Okay, there's a choice of a constant in the metric which you can choose freely. Okay, so the solution takes this form. It's minus 1 minus 2 gm by r dt square, 1 minus 2 gm by r inverse dr square, plus r square d theta square plus r square sine theta square d phi square. Okay. This part is the same. Okay. This part is the same as what you had in regular polar coordinates. This part is new. Okay, this part is new. Okay, 1 minus 2 gm by r and 1 minus 2 gm by r inverse. Okay. So let me just say a couple of things. One is this is the unique solution to Einstein's equations. Okay, I've not shown this. You can look up the proof in Sean Carroll's book, satisfying the three conditions that I listed above. Okay. Here m is an arbitrary constant. Okay, so although I've written it as 2 gm by r, you can think of gm as some arbitrary constant. Okay, because there is no g that's appearing when I solve the equations, right? When I solve the equations, I'm solving the vacuum equations. The only place that g appears is on the right hand side, g times t mu. Okay, so this gm is really, I can think of it as some constant c. Okay, for every choice of this constant c, this is a solution to the Einstein's equations. So I get a family of solutions. By varying m or equivalently varying c, I get a family of solutions. Okay, now you can see something interesting. Let's look at the limit of this metric where r is much greater than 2 gm. Okay, r is much greater than that constant. In that limit, okay, you can take this particular term 1 minus 2 gm by r, okay, and you can do a Taylor expansion. Okay, you can do a Taylor expansion and keep terms to first order in 2 gm by r. Okay, so what you will get is 1 minus 2 gm by r and 1 plus 2 gm by r. Okay, after the Taylor expansion, dt square dr square, r square d theta square plus r square sine theta square d omega square. If I switch to Cartesian coordinates, that is, if I switch in my standard way from r theta phi to x, y, z, what I will find is that the metric is in this form: 1 minus 2 gm by r dt square, 1 plus 2 gm by r dx square plus dy square plus dz square. Okay. Now you see that this is exactly the form of the metric that we had in the weak field approximation. In the weak field approximation, we with sources that give us Newtonian gravitational field at large r, okay, we saw that we had exactly this kind of potential. Okay, we had exactly this kind of potential in the weak field approximation. So it makes sense to write that constant in this form. Okay, instead of just writing c by r, it makes sense to use 2 gm by r, because in the weak field approximation you get exactly what you expect at large distances. Okay, and so this m now has the interpretation of mass. So if I'd written 1 minus c by r, and if I'd written c is 2 gm, m would now give me the correct interpretation of mass when I look at this at large distances. Okay, so m is equal to 0 gives, so you have a family of solutions with all values of m. M is 0 gives Minkowski spacetime as a special case. Okay, because if I just plug in m is 0, I'll get back my standard Minkowski solution. Okay, so and Minkowski spacetime we know already has these isometries, right? It has the time translation invariance and it has rotation invariance. If you set m is equal to 0, you get additional symmetries. You get boosts, okay, and you get you get boosts, okay, as your additional symmetries, and you get translations in x, y, z, which you don't have with this solution. Okay, r is equal to 0 is a special point of the solution. Okay, for general m. Now here are some key points. Okay, which is, one is that the Schwarzschild solution is exact. Okay, it's not an approximation; it's exact. This in the limit r greater than 2 gm, it agrees with the weak field approximation, but this solution with the original 1 minus 2 gm by r inverse, this is an exact solution to Einstein's equation. Okay, you can plug it into Einstein's equations to just check this. Okay, instead of trying to derive this, you can just check this by plugging it into g mu nu is 0, and you'll find that it's an exact solution. Okay, and again, we've seen that exact solutions are very powerful, right? Because once you have an exact solution, if you have a setup which corresponds to this exact solution or perturbations around it, you can do perturbation theory around this to find what happens around this. Okay. Uh, but the one important point is that the Schwarzschild solution, I'll just abbreviate it as SCH from now on. Okay, it's found by solving Einstein's equations locally. Okay, which means you're solving a differential equation. You don't know what the solution is over the entire manifold. Okay, you solve at one point, okay, or some neighborhood, and you have to evolve. Okay, or you have to solve the differential equation and extrapolate to the rest of the space. Okay, by maybe matching to some boundary conditions. Okay, so what is a boundary condition? Our boundary condition is that asymptotically we're saying our space is Minkowski. That is, if we go to large R, okay, R goes to infinity, we get approach Minkowski spacetime. So you can see that the Schwarzschild solution indeed approaches Minkowski spacetime at large R. Okay, that is, this goes to 0, this goes to 0, and you get Minkowski spacetime at large R. But now the question is, so imagine that we're solving at large R, we get Minkowski spacetime, but we're solving a differential equation. So our solution, we now have to extrapolate towards R is equal to 0. Okay, and we're assuming that the Schwarzschild solution, which emerges from solving this differential equation, works all the way to R is equal to 0. Okay, why would it not work? Okay, let's see why it would not work. Okay, so one problem that you see right away is that at R is equal to 2gm by c square, you run into a problem. Okay, in the weak field approximation, we never worried about this problem because we said that this term is always small. You have, for the weak field approximation, you must be at R much larger than 2gm. But now we're saying that this is an exact solution. So we should be able to extrapolate it to small r. But at small r, you run into a problem, right? Because now if I get to R is equal to 2gm, this becomes 0. Okay. We were looking for solutions which have non-degenerate metrics. Okay, that is where the metric doesn't have 0 eigenvalues. The metric should always have -1, +1, +1, +1 as the eigenvalues. Okay, so this is a problem. Okay, or this becomes degenerate. This is even worse. This component of the metric becomes infinite. Okay, as you get to R is equal to 2gm. Okay, so this seems like a problem. Okay, that is, you can't really extrapolate the solution from infinity. You can't come in beyond R is equal to 2gm. You have to stop here. Okay, so now the point is, what does it mean that you have to stop here? Okay, that you can't go beyond this point. Okay, well, let's recall what happened in Rentala coordinates. Okay, in Rentala coordinates, our metric was of this form: ds square is minus rho square d eta square plus d rho square plus dy square plus dz square. And it appears that if you go to rho is equal to 0, you have a degenerate metric. Okay, that is, one eigenvalue is going to 0. But if you look at your Rentala coordinates, okay, rho is going to 0 means that you're going to the asymptotically to the hyperbola, which is on the Rentala horizon. Okay, but that Rentala horizon itself was not part of your Rentala coordinate chart, right? You cannot smoothly include that in your Rentala coordinate chart. So if we switch to Minkowski coordinates, we see that there's no problem crossing this Rentala horizon, right? You can always cross the Rentala horizon. Your coordinates are valid beyond that. Okay, your Rentala coordinates are only valid on a patch. They're not valid as I cross over into this region. So when solving Einstein's equations, the point is that you have to choose a coordinate system. But once you make the choice of that coordinate system, you don't a priori know that your coordinate patch can be extended over the entire manifold. Okay, so even though you started with a solution at R is infinity, and you started with some tr theta phi coordinates, you don't know that I can extrapolate this tr theta phi to cover the entire manifold. Okay, so this is a problem. Okay, so now you've run into a problem, which is that at 2gm you have some trouble extrapolating your solution. Okay, at R is equal to 2gm, you have trouble extrapolating your solution. Okay, now is this a genuine problem, or is this a problem of which will go away if I change my coordinates? Okay, so for example, if in Rentala coordinates, we know that if you switch to Minkowski coordinates, there's no problem. You can continue, okay, talking about space-time points behind the Rentala horizon. Okay, you can go beyond this. Okay. You can go beyond this. Okay, so R is equal to 2gm. Okay, R is equal to 2gm is called the Schwarzschild horizon. Okay, it's actually very similar to this Rentala horizon. Okay, so when you cross this horizon, can you cross this horizon by a suitable change of coordinates? That's the question. Okay. Now the answer is, as long as nothing physical is becoming infinite. Okay. For example, the curvature is not becoming infinite. Okay. You should always be able to find a coordinate system which will go beyond this. Okay. So for example, the problem that you're running into at rho is equal to 0, this is called a coordinate singularity. Okay. It's not a physical singularity because the curvature, if I compute the curvature, for example, if I compute the Ricci scalar, I would find it 0. If I compute the Riemann tensor, the Riemann tensor is 0. Okay. In Minkowski spacetime. Even if I compute it in Rentala coordinates, I would find it 0. Okay. The Riemann tensor is 0. So as long as the curvature is actually 0 or finite, okay, you should always be able to find a coordinate transformation that can take you beyond this coordinate singularity. Okay. So what we can do is to check if the singularity that we're encountering in Schwarzschild coordinates is a physical singularity, or if it is just an artifact of the coordinate choice that we're using. Okay, we can compute the curvature. Okay, we can compute the curvature in the limit that r approaches 2gm. Okay, in the limit that r approaches 2gm, let's compute the curvature. Okay, and since the curvature is a tensor, okay, it's better to compute scalars. Okay, because scalars, the components of the scalar don't change if I change the coordinate system. So we'll compute, let's say, the Ricci scalar, or we can compute r mu nu rho sigma, r mu nu rho sigma. Okay, this is also a scalar, and their values should be the same at a given point on the manifold in any coordinate system. Okay, so for example, if we compute this quantity r mu nu rho sigma, r mu nu rho sigma, what we would find is that this evaluated at any point on the manifold in the t, r, theta, phi coordinates, okay, would be 48 g square m square by r to the 6. Okay, you can show this. Okay, so what this means is the point r is 2gm. Okay, it does not have infinite curvature. Okay, which means in principle I should be able to go beyond r is equal to 2gm by a suitable change of coordinates. Okay, now strictly speaking, you should not use these coordinates. That is, you should not use the coordinates r theta phi, t r theta phi, to go beyond r is equal to 2gm. You should change your coordinates. Okay, but suppose we don't change our coordinates and we still go to r is equal to 0. You can see that you would run into a problem. Okay, that at r is equal to 0, the curvature would become infinite. Okay, this curvature is actually becoming infinite. Okay, at r is equal to 0, the Schwarzschild it does have infinite curvature. Okay, this kind of infinity where the curvature is actually blowing up as you're approaching a point on the manifold, this kind of singularity is a physical singularity. It's telling you, your solution to Einstein's equations is telling you that something physical, the curvature of the manifold, is becoming infinite at a point. Okay, now you can't really use the tr theta phi to see beyond the horizon. So what we'll have to do is, before we can really claim that there is this curvature singularity at r is equal to 0, we will first have to switch coordinates to go beyond the horizon. Okay, we'll have to switch coordinates to go beyond this horizon. That switching coordinates we'll do next time. Okay, right now we'll study the solution outside the horizon. Okay, we'll study the solution for r greater than 2gm plus. Okay, greater than 2gm. So this solution is valid all the way from r is infinity all the way to 2gm, just above 2gm. So I'll denote it as 2gm plus. Okay, so 2gm plus any little epsilon. As long as epsilon is positive, my solution is valid. Okay, in this tr theta phi coordinates. So what that means is, even if I have a very compact object like a black hole or a neutron star, which is compressed to a size r less than 2gm, okay, so it's compressed within some capital R. Okay, it's compressed within some capital R, and this capital R is greater than 2gm. Okay, so 2gm I've denoted over here. Okay, this capital R is denoted over here, and I'm looking at the metric at some point r which is greater than capital R. Okay, so even if I have a sufficiently compact object, it doesn't have to be a weak field approximation anymore. The gravitational field doesn't have to be weak. I could be close to a neutron star or close to a black hole. As long as I'm outside of this rs is equal to 2gm, okay, I can still describe, and as long as I'm outside the object, locally, the metric here is 0. So I'm really solving the vacuum for vacuum Einstein's equations, okay, because there's no source over here. The moment I enter the object, that is, so for example, if I'm solving for, let's say, around the sun, the moment I enter the sun, okay, these equations are not valid because there is a source, okay, which is the material of the sun itself. But as long as I'm outside the sun, this metric gives me the exact solution to Einstein's equations. Okay. So even for the sun, if I'm at radii which are greater than r, which is greater than the Schwarzschild radius, the radius of the sun is 700,000 kilometers. The Schwarzschild radius of the sun is 3 kilometers. So outside the sun, I am now getting an exact solution to Einstein's equation. This is not a weak field approximation anymore. This is an exact solution. So I have an exact non-perturbative solution to general relativity. And what you can do now is with this exact solution, now that you know the metric, okay, you can find the motion of some test object, okay, in this metric in order to determine the trajectories, okay. And this will give you the full general relativity prediction of what should happen when you have a spherically symmetric object. The sun is close to being spherically symmetric, okay, approximately exactly spherically symmetric. So we'll get an exact solution, okay. In the weak field limit, that is if r is much, much greater than 2 gm, we've seen that you get Newton's laws, okay, you get back Newton's laws. But if we keep the full metric, that is if we keep the full Schwarzschild metric, that is you don't approximate this as 1 plus 2 gm by r, okay, then you can find the geodesics, okay. This, for example, the path that Mercury travels, the path that the Earth takes, okay, all of these paths you can now find exact solutions for their trajectories, okay. Those exact solutions will not be exactly the Kepler orbits, okay, these elliptical orbits that we derived in Newtonian gravity. They will be modified, okay, and we will be able to work out exact orbits, okay. Of course, the exact effect of the orbit will be more important if you are closer to the sun, okay, that is you are further away from the weak field approximation, okay. The Earth is, to a very good extent, the weak field approximation works, but for Mercury, the corrections to the weak field approximation are important, okay, and we have an exact solution to what should happen to Mercury's orbit, okay, if we work out the geodesic equations. So in the next class, what we'll do is we won't really solve the geodesic equations. It's a lot of algebra, okay, but I'll just show you the path to working out a solution to the exact Schwarzschild solution, okay. So this is going to be really powerful, okay. So let's just recap the ideas. Symmetries are a very powerful idea. So if you demand symmetries, they highly constrain the form of the metric. We demanded rotational symmetry. It turns out when you demand rotational symmetry, you automatically get time translation symmetry for free, okay, as a solution to the vacuum Einstein's equations. There turns out to be only one class of solutions to the vacuum Einstein's equations, which are the Schwarzschild solutions. All of them differ by just a choice of this constant, which is m, okay, which you can interpret as the mass of the object. Now, this is an exact solution to Einstein's equations, which means that you can exactly predict orbits of planets, and you should see deviations from what you predict just with Newton's laws alone, okay. The effect will be most important for planets which are closest to the sun. We're looking at Mercury, okay. Mercury is going to have the biggest effect, okay. So again, we probably won't have time to work out the exact details of the effect on Mercury. You can look it up again in Sean Carroll's book, but I will work out a little bit about the geodesic equations because that is a little bit informative, okay. So we'll do that in the next class. So, and the other thing that we'll do is we'll go beyond the horizon, okay, this R is 2 gm, and as we go beyond the horizon, we'll see that you really do encounter a physical singularity. The curvature does blow up at some point, okay, and that will correspond to a black hole, okay. There'll be a physical singularity, and we'll discuss the interpretation of what that singularity means, okay. Okay, so we'll stop here. Any questions, last minute questions? We can take 1 or 2 questions before we stop. Any questions online? Okay, if not, let's stop here. Okay, see you on Thursday. Yes. Given a set of killing vector fields, how do you solve it better? I don't think there's an easy way or a guaranteed way to solve for it. But one thing that you could do is you could choose a coordinate system in which one of the killing vector fields is partial theta, like partial x. then the metric should be independent of that x. Right? If I choose one of the killing vector fields as this, then the metric should be independent of x. So that's essentially what we did for the Schwarzschild metric. Roughly speaking, partial t, partial theta, partial phi are killing vector fields. Okay, and therefore what you can do is you can, by going to polar coordinates. Okay, your metric can only depend on r. Your metric coefficients can only depend on r. Partial theta? Yeah, that's right. So you, okay, so yeah, that's where I was not really precise. Partial, so at least you know it doesn't depend on t and phi. Okay, partial theta is not a killing vector. Okay, and it's not actually possible. Yeah, because it's not really possible to go to a coordinate system where all three killing vectors just correspond to coordinate directions. Okay, so you can't really go to a coordinate system where all the killing vectors are, yeah, in fact, see, yeah, the reason is xy is equal to z, yx is equal, sorry, x is equal to y, right? If you choose one of them to be a coordinate vector, the other ones are automatically not coordinate vectors, because if the other one was also a coordinate vector, their commutator would be 0. Okay, so you can only choose one of them to be a coordinate vector. Okay, that's similar to in quantum mechanics, how you can only diagonalize Lz, you can't simultaneously diagonalize Lx and Ly. So similarly, you can only choose partial t and partial phi to be killing vectors. The other killing vectors you have to sort of figure out, but at least this tells you that your metric doesn't depend on t and phi. Okay, and then you can, okay, then it's a little work to show it doesn't depend on r and theta. Sorry, it doesn't depend on theta. And then if you're solving Einstein's equations, then the only unique solution is that particular r dependence which we found for the vacuum Einstein's equation. So just the killing vectors alone do not specify the full metric, but for a maximally symmetric space, the killing vector fields uniquely specify because you have so much symmetry that it constrains the form of the metric. Okay, and then you can uniquely fix the metric. But if you only have partial symmetry, that is, if you don't have this maximal symmetries, then it only tells you certain constraints that the metric obeys, but it doesn't tell you uniquely what the solution is. So for example, if I don't demand that the metric solves Einstein's equations, the more general solution will be of the form e to the alpha r dt square plus e to the beta r dr square plus r square d omega square. Okay, but this function and this function are a priori independent. Okay, only by demanding that they solve Einstein's equations does the solution become of the Schwarzschild form. Okay, thanks for the question. Let's stop.